Now, this is where we have completed the first part, the formation of the universe and all the theories related to the formation and the basic understanding of the universe. Now we come to the next part of our lecture, and in this part of the lecture, we'll discuss about celestial bodies. We'll understand various kinds of celestial bodies, what they are, how we define them, and we'll try to understand from the point of view of examination how they can be important. So we are going to discuss about stars, nebula, planets, satellites, asteroids, comets, and meteoroids. And we'll discuss about meteors and meteorites as well. Now, first of all, star. When we talk about a star is a body, kind of a round shaped body, which has a lot of energy at its core. There are nuclear reactions going on at the core, and because of these nuclear reactions, they are able to produce their own heat and light. So, a celestial body that generates light by nuclear reactions, or we can also write nuclear fusion reactions, and is held by its own gravity can be called as a star. So the best example is our sun. Our sun is a star. Similarly, you have n number of stars in the universe. There are billions and billions of stars which are present, and all these are the stars which can generate their own heat and light because of the nuclear fusion reactions that are happening at the core. This nuclear fusion reaction will be happening at the core of a star, and it is held by its own gravity. All right. Now when it comes to the star, it's important to know how the classification of the stars happen. There are two major ways in which the classification happens. One is on the basis of the temperature of the star, and second is on the basis of the size of the star. So temperature and size, and that's why if you look at the names of the stars, they are called as red giants, or they are called as white dwarfs. So one part is the color and the second part is the size. The color comes from the temperature. Now just look at your daily life. All right, let's say if we talk about LPG cylinders, they often, you'll see that they will be burning with a blue flame. Correct, they'll be burning with a blue flame. If you look at a matchstick basically burns with a yellowish flame. If you compare these two to a burnt coal or a burnt wood, you will see that they are reddish in color. So what's the difference? The difference is in the efficiency and the temperature. LPG gas cylinders, they have blue flames. Any heat source that is blue or white in color, they would always have a higher temperature. If it is yellowish in color, moderate temperature. If it is reddish in color, lower temperature. All right. So something that you observe in your daily life can also be extended to the stars. Stars which are blue in color, they have the highest surface temperature. Stars which are red in color, they have the lowest surface temperature. So on that basis, the classification can be done. Red, orange, yellow, yellow white, white, white blue, blue. Surface temperature more than 30,000 Kelvin in case of blue, and surface temperature only in the range of 2400 to 3700 Kelvin in the case of a red star. So if I say a red giant, if I'm using the term red giant, red would mean what? Red would mean low temperature. Correct? Red would mean low temperature. Then we have the second term, giant. So giant comes on the basis of size. That you will have super giants, you have giants, you have main sequence stars, you have white dwarf, and you have neutron stars. Main sequence stars are the average size stars. They are average sized stars. Then you have white dwarf and neutron stars are the smallest. Super giants are the largest. All right. So on the basis of temperature and size, we do this classification. So if I revisit a star which is called as red giant, it would mean that it has low temperature, and giant would mean that it has large size. It has large size. Now also remember that from size also comes luminosity. That if a star has a larger size, it also has larger luminosity. So just remember that these two are related. Luminosity is not related to temperature. Luminosity is related to size. All right. So large size would also mean that luminosity of the star is high. So on the basis of the temperature and the size, we have this diagram which is called as Hertzsprung-Russell diagram. This basically tries to map all the different kinds of stars that we have in the universe. So for example, if you see this side, you have the supergiants, you have the giants. Then because here what you see, that the size is increasing, luminosity is increasing, so the size is also increasing. So you have the supergiants and the giants here, and you have the white dwarfs here, because low luminosity means also that the size is small. So on this scale you have temperature. All right, so here you have the highest temperature and this side you have the lowest temperature. So that's why this is blue and that's why this is red. Correct? So basically, to map all the different kinds of stars, this particular diagram is used. Not really important for your examination, just that for the depiction purpose I've used this diagram. Now the next topic that we come to is formation of a star. Now stars basically originate from something which is called as a nebula. Now these nebula are, you can say, nothing but cluster of dust, gases, etc. that have just come together as a cloud. Now from here the formation starts. That this cluster that you have, this cluster will start to come together. This cluster will start to form a kind of a core. And this is where we'll see that the gravity pulls together the dust and the gases from the nebula and a protostar is formed. So protostar, nothing but you can say, is like a core, the core of a star. From there we see that because once the core is formed, it will have the gravitational force of its own, and everything that is there in the vicinity, everything that is there in the surrounding, they will start to come together. They will start to come together, close in on this particular star, and ultimately we'll see that a larger star will be formed. So these clouds of dust and hydrogen gas then collapse under their own gravity. The center of this cloud becomes very hot and nuclear fusion occurs, and this process releases so much energy that stars then shine with their own light. So ultimately what has happened? First nebula. From nebula, they coming together as a cluster, as a cloud. Protostar is formed. There is a core that has been formed. It has its own gravity. Because of that, it brings in all the things that are there in the surrounding, and ultimately the star formation happens. All right. So this is how the formation of a star would happen. One thing that is very, very important for us is to understand the life cycle of a star. Now, this is a common misconception that if a star dies, it will form a black hole. All right. So let's say one of the statements in your prelims examination says that when the sun dies, it will convert into a black hole. Let's say there are four statements that have been given about a star or maybe about the sun. And in that, one of the statements says that if our sun dies or whenever our sun dies, it will convert into a black hole. Now, just remember that this is a false statement. Some of the stars will definitely form black holes, but not all the stars. All the stars will not form black holes. Please be very sure about this. Now, what happens is stars originate from something which is called as a stellar nebula. All right. This is a kind of nebula which will convert into a star. That's why it is called as a stellar nebula. Now, this stellar nebula can take two courses. Either it will develop into an average star or it will develop into a massive star. Now, how do we determine what is a massive star and what is an average star? So this is where something which is very famous comes in, and that is Chandrasekhar limit. Now, what Chandrasekhar limit says, that if the mass of a star is more than 1.44 times the mass of the sun, if mass of a star is more than 1.44 times the mass of the sun, then in that case it will be called as a massive star. If it is less than 1.44 times the mass of the sun, in that case you will call it as an average star. All right. So if you have an average star, when the average star dies, it will convert into a red giant. This red giant finally will be destroyed and it will collapse into something which is called as a planetary nebula. Just remember that it has nothing to do with planets. It is just named as planetary nebula. And ultimately, the core of this planetary nebula will be left out and it will ultimately convert into a white dwarf. So the final stage of an average star will be white dwarf. So if the statement in your prelims examination says that when our sun dies, it will convert into a white dwarf, then this could be a correct statement. But if it says that it will convert into a black hole, wrong statement. So what will convert into a black hole? Let's see. Massive star, when the massive star dies, it will convert into red supergiant. Remember red because the surface temperature is very low, and supergiant because the size is very big, the biggest. Now, ultimately what happens is that the core of this red supergiant becomes very unstable. And because of this instability, ultimately the core collapses. And there is a huge explosion that happens at the core. And this huge explosion that happens at the core, this is called as supernova. This explosion is known as supernova. So ultimately supernova will happen, and even after this, there is no guarantee that this massive star will convert into a black hole. It may or may not. It either may convert into a black hole or it would convert into a neutron star. What is a neutron star? Just remember that we discussed that it is the smallest kind of star that we know. So, if let's say, again, I'm going back to the same question. Let's say the statement said that when a massive star dies, it will convert into a black hole. Even this is a false statement, because it will, we cannot say, it can convert into a black hole. It may or may not convert into a black hole. It may either convert into a black hole or it may convert into a neutron star. Both the possibilities exist. All right. So that's why this is the life cycle of a star. So just remember what course, what kind of star takes, and that's why Chandrasekhar limit becomes very, very important. Let's look at this particular question. This was asked back in 2009 question paper. Who of the following scientists proved that the stars with mass less than 1.44 times the mass of the sun end up as white dwarf when they die? So this is something that was given by S. Chandrasekhar, and that's why this number was said to be Chandrasekhar limit.